You didn't like the, okay, there was a squared, but also you didn't like the number in front, right? It was a modified x method, true? So in number 29, before we get to 32, he was the end of that section, and he's harder because he has a cosine and a, if they're all signs, it's okay, because I can just do a modified x method and think of 3u squared minus 5u plus 2. I heard multiple ones of you that was, I tried it and I got stuck. Where do you go from here? Just factoring, just the algebra, not the trig. Yeah, you think about a 6, right? Some of you did 2 and 3 and you got it wrong because a negative 2 and a negative 3 will make negative 5. Oh, never mind, that was right. Which one am I thinking of? Oh, thank you. Negative 2 and negative 3 would make negative 5, but it would make a positive 6. So if you did 2 and 3, you weren't wrong. Well, you were. But it was so close to being right. Instead, you needed to do negative 6 and 1. Yeah? And once you did that, I mean, you could have done the modified x method where you go ahead and put a 3 and then you get your final answer. Is anybody actually doing that with the star? Yeah, just a couple. So you could have thrown in your 3. And then you would have gotten your, let's see, u minus 2 and then your 3u plus 1. You could have done it that way. Or you could have done the old-fashioned way of grouping with a negative 6u and grouping with a 1u, and then you would have had your minus 2 and your 3u squared. Group, pulling out a 3u, pulling out a 1, you get that guy. What's left is a u minus 2, either way. Some of you box people, you could have gotten there too. But long story short, for number 29, before we get to this one, you would have ended up, and remember, multiplication is commutative, so either way, you just needed to get that sign of x back, oh, that's gross, that sign of x back in. Then you're done. But it was just a straightforward factoring problem if it's all in terms of sign, which it is. So, number 32, what's different? This one's cosines, that's good. This one's, oh, that's a whole other mess. But this one has sine and cosine. So what did you guys see in the answer key just a second ago about how they remedied that? Sorry, I just started recording a second ago, so there's 2 and 4 and 6 filling in formulas. Here we go. Where did they start?
They started with the
They had to get it. Pythagorean identity. They had to get it in terms of cosine. Once it's in terms of cosine, now, who likes a negative in front of a factoring problem? Nobody ever. So what did they do? Factored it out. And then they were able to just look at the inside. The negative gets to chill on the outside. Oh, and this one's even easier because there's no number in front, but it was hard the first step. Yeah, negative 4 and a positive 1 makes sense. But you could have done your x method if you wanted to. This just didn't need any further work because it's a simple x method. Are we okay? There was another even, number 48, is that right? Although for some of you, number 48 might have been easier because there was obvious, well, if you looked at the examples from yesterday, there was obvious math to do. If you had your formulas in front of you, you could have made that 1 over secant and that 1 over cosecant. You couldn't have done a Pythagorean because there was no squared. Super illegal if you tried. There's no squared. I cannot use a Pythagorean. But you could have tried making him 1 over secant, 1 over cosecant, but that makes it so much worse. Why not get a, what they do? Get a common denominator. Why not get a common denominator? Did anybody kill a puppy? Or did you spoil it? You can't just distribute a square. That's not how they work. We totally did yesterday. You can't distribute a squared over addition or subtraction. Sorry, Justin was right. There is a distributive property of powers, but not with addition or subtraction. I have to FOIL. Whoop! Had it. Did anybody get lost in this stuff? It's the way you see it, right? How'd they do it? Cosine squared plus sine squared is So this is 1. Remember, all addition can be switched around. That's 1. What's 1 plus 1? And now I can, like Emma did yesterday with under the square root 1, factor out of 2, and then I can, done. Now remember why we're doing this. 5.2 and 3, and 4 and 5 and 6. In 5.3, they're going to give us this mess and say equals 2. Yeah, sure. Equals 2. And we're like, some of you would start subtracting, but still common denominators have to be a thing. If you can make this side look like that, oh, that's so much easier than that. It's in your best interest to try to make these nasty things look better. But to make them look better, you got to use trig. If you guys want, you can go up to the Calc PC kid and be like, we're learning how to use trig identities because they're learning how to use them too. Just, well, in a lot harder ways. Can I show it to you? There's a very tiny piece of a problem they're doing up there on the board, but I don't think you see your trig identities anywhere. Oh, you do! Do you see a trig identity up here that made everything possible? I mean, you won't understand almost any of it, but there's one thing you can understand, and it is a key to solving the whole thing. Anybody? Can you find the one thing you can understand?
The tangent SEC symbol there.
Now here's the crazy thing. You ready? Their original problem, it's called an integral problem. It has this little like elongated S summa. It's called an integral sign. Their original problem had no trig. None. It had square roots and x's and numbers. No trig. But the only way to solve it is to somehow, let's not even talk about that today. If you're curious, come show me, or come find me, I'll show you. But the only way to solve the problem is to put trig in. And the only reason you would ever put trig in is because all these identities show us that if we have trig, we can play and make it look different. If we have x's, we're stuck with, well, we do whatever math we can, but then we're done. If we have trig, we can change what it looks like, and we can basically make the impossible possible. Super crazy, but you could understand. Anyway, any more evens that you guys need to see? No, I guess. Any other odds we need to talk about? We already did 29. Anything else though that we got stuck on? You sure? I know some of you have questions. You commented. Yeah.
7.
Okay, cool. Let's go look at it.
Pages.
Section 5.2, homework is in Google Classroom. If anyone's bored, you want to write that down, totally fine. We're going to go peek at number 7. Can I just clear all of this? Is that cool? Clear stuff. No. Sorry, everything updated over break, so I can't find. Oh, here it is. Right? I don't even know what the clear symbol is. I'm just going to go over here and find number 7. Okay, here he is. Okay, yeah, these ones are like totally out there in the sense that we didn't really do examples. Sorry when that happens, guys. Usually if something shows up where you're like, I have no examples in my notes like this type of problem, it's probably kind of what I thought would be review. It doesn't necessarily help you, though, if you're stuck on it. On this one, well, here's your classmates. Question, that works. You guys are looking at your homework, right? What did you do? Yeah. So what they're asking is find the values of all 6 trigonometric functions. So what they want is we have so, ca, we're missing coa, so they want tangent as far as what we're trying to find, and then they want cho, cosecant, sha, secant, cow. They're saying find all of them. We have 2, we need to find the rest of them. So there's so, ca, we need coa, tangent, and cho, sha, cow, cosecant, secant, cotangent. And so Nathan's like, it kind of reminded me of the cheater chart, so I just kept going with that. So for him, in his mind, I'm guessing that you were on the pi over 6 angle, and you remember that 1/2 is sine, square root of 3 over 2 is cosine. What's tangent then? Square root of 3 over 3. But remember, there are these old trig identities that say, oh wait, no. They're quotient. Tangent is sine over cosine, so we could have actually just taken these two and divided them. And that would have gotten us that same answer because we would have had sine over cosine. So you're kind of using your identities, Vanessa. Just it's kind of also the unit circle. It's a little bit of both. 1 over rad 3 would have needed to be rationalized. So you could have gotten this a couple different ways. But then as soon as you have all of these, remember the reciprocal identities say cosecant is flipping him. Oh, sweet. Secant is flipping cosine, 1 over cosine. But when I flip, I have to rationalize. And then cotangent is flipping this guy. Which, maybe you remember, he's the other guy. We could eventually be this guy over that guy. So some of you might have been like, this is so random. It's unit circle all over again. But you're using reciprocal identities to know to flip, or quotient identities to know to divide. So you're kind of using the identities in an application. Does that kind of make sense? Anything else that was weird or different or you didn't know how to keep going? Yeah, 51 is over here, the latter end of homework. You should be kind of like our examples yesterday. Oh my goodness, come on. That's not good. I just lost him. Sorry guys, I totally lost the homework. I tried to go too fast. Where are you, homework? There you are. 51 is the next page. Oh, not like what we did yesterday. They're saying to actually throw this nasty guy into a graphing calculator. To be honest, which might be weird for some of you, but it might not be for others of you. I think going to your calculator is way harder than just doing it. But if you wanted to go to your calculator, then you would have literally just put in y equals cosine of x. Remember, there's no cotangent button, so then 1 divided by tangent of x plus sine of x. And what they were asking, or what they were telling you, which you probably didn't know from the directions, but what ends up happening is it looked like a super basic, it should have looked like a basic trig function and been like, wait a minute, that whole thing is just, but who is he just? Well, to be honest, I'm lazy and don't want to go find a graphing calculator, so I actually like this better, which is just doing it the way that the rest of homework goes, which is getting cosine squared plus, I would get a common denominator, sine squared. Hey, it's cosecant. You're supposed to, when you graph it, just see a cosecant graph and be like, oh, it's not super complicated, it's just cosecant. That's why they had you put it in your calculator. It's like, oh, look. But technically, if you had just done like our homework, you would have gotten cosecant. But that's weird, huh? You're lazy, so you don't want to use your calculator? Or at least I'm lazy, so I don't want to use my calculator. But it depends. What's work to one person is pleasure to someone else. Anything else from homework? Last call. How did we do on these? The test type of problem that people always get wrong, but I had you guys pay super close attention to yesterday? Did we get it? You skipped that one? Which one did you guys have? 55. 55? It wasn't that bad, was it? Walk me through real fast, just because some of you might have done it illegally. Plug in. And what do you get when you plug in, Sway? You can do mental math. Yeah, and squaring square root of.
Parentheses 2 secant theta and close parentheses squared.
What happens when you square that then? We're skipping a step. Or secant squared theta, yeah. Tag team, it's okay. Okay, now what? Emma, this was yours yesterday. Where do we go next? Got it. But it's still under the square root, right? And then because we can't go distributing the square root. That's killing puppies, right? Oh, hey, and it's on the board over there. What is secant squared of x minus 1? Tangent squared. And what's the square root of a squared? And then if they're really snazzy and mathematically proper, they would put an absolute value because the square root of the square is an absolute. Just be careful of PEMDAS. Be careful of correctly factoring. Be careful of killing puppies. That was the one I missed. Careful of the basics. Okay, sorry. I just want to make sure I have properly shown that and warned you guys of that one because once again, everyone makes mistakes on that. But we got to get back to notes. Section 5.2. I gave you a peek at it yesterday. Section 5.2 isn't as ambiguous. Whoops. Whoa, 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 whoa. Too excited. Lo Santo. Section 5.2 is not as ambiguous. Don't worry. I'll get back to the beginning of notes. Those of you that might have been gone yesterday, we didn't do tons of crazy work. I just showed them one example, what's coming, and then we're going to take notes on it. But section 5.2, the directions are different. They're not just like test your skills. Can you do stuff with trig? Can you do the math? Can you plug in identities and start changing things? But section 5.2 says, this statement is always true. Show us how. This side will always equal this side. Show us how that's true. So the cool thing is, you already know the answer. Every single problem in and of itself is a question and an answer. So to be honest, tomorrow when I go to grade, if you guys noticed just a second ago, I scrolled down to 5.2. There were no evens shown. Why? You know the answer. Make him look like him, or make him look like him. Make one side look like the other. That's the question and the answer all at once. The why? Well, once again, it's building your skills of, hey, once we have trig, a whole new world opens in the sense that we can play and change and transform and make things look different. Section 5.2, the directions. Remember, honors the first day back, we were recapping, we were reviewing all of chapter 5 thus far. 3 main words from the beginning of chapter 5. 5.1 is simplify. Can you learn how to simplify trig stuff? 5.2 is verify. Verify. Can you show that this always works? And 5.3 is solve. Can you apply all of your other skills to actually get answers to crazy equations? And I'm going to zoom in on the first page. You guys see lots of words, but hold on. That chart, that table that's up there, it's from the book, number 1. And number 2, you don't need to memorize all those words. It's more of a, okay, keep these things in mind when you're trying these problems, and I'll just highlight the most important parts. Does that sound good? So don't go frantically trying to write down the whole table. It's not that important. It's more of an approach, an idea, things to keep in mind. So let's zoom in. And zoom in. Okay. You guys can't even see the title. I'm sorry. Verifying trig identities. I'm going to show you what's coming. And okay. What's coming is 5.3. But where we are is 5.2. What's coming is conditional equations. And conditional equations are going to be like, hey, can you solve for me? What's that one we just had? That ended up being 2 secant, but it was something nasty to begin with. Oh, we could have done that one. Okay, yeah. That one ends up being 4 absolute value tangent, right? Or 2 absolute value tangent. So that was 4 secant squared of x minus 4. Yeah, got it? And it ends up being 2 tangent. Okay, so it ends up being 2 tangent absolute value. equals 2 rad 3. That is a conditional equation. That is a, ready? Here's the key word for conditional equations. That is sometimes true. Not always, only sometimes. That was the one that we were just working on, the number 55. There we go. That whole bluff becomes 2 tangent, so I can divide both sides by 2. Tangent equals root 3. Is that sometimes true? Yes. Unit circle. Square root of 3 over 3, 1 square root of 3. Sometimes tangent is root 3. Is tangent always root 3? No. It can be all sorts of different stuff. He goes forever low, forever high. Tangent is the guy who can be anything. Only at certain places, but he can be anything. Sometimes true. You would need the unit circle. Some of you know thereof. They are, or tangent is pi over, at pi over 3, root 3. Tangent equals root 3 at pi over 3. We would need the unit circle to finish that answer. And our answer would look like, in this one, our answer would look like something to the effect of x equals, and then all sorts of different answers. However many they want. Maybe they want infinitely many, so we have to do some sort of like formula to say, hey, this and all of its coterminals. But an identity, where we are at in section 5.2, is very different. An identity is something like tangent is not sometimes root 3, but tangent is always sine over cosine. That's always true. Sometimes true, we have to actually go explain, oh, this is true for these conditions. Identity, that's always true. But what section 5.2 is telling us, okay, these always true statements, show us. Show us that you could do it on your own. Not for the point of someday you're going to be handed a T-proof and being like, live or die, can you show it? No, that's not the point. But I'm showing you in multiple levels of calculus down the road, you're going to have a problem where if you can't take one statement and substitute it with an always equivalent identity, or you can't transform it, it's going to be an impossible problem for you. Sure hope that's not 1 out of 4 questions on a midterm worth 25% of your grade. Just kidding. Math tests in college usually at least have like 10. Although there was one test I only had 2. And I didn't turn it in because I didn't know either one. But the final replaced the lowest test. I just put it in the trash as I walked out the door. I wasn't the only one to do that year. Just this one professor always had that policy, and so if you got to a test and you studied the wrong ones, you're like, sit there for a bit. Anyway, don't worry. Ended up still getting an A because of that final, but that was rough. That was a hard day. You don't want to get to a problem and then not be able to go through it, or at least not be able to do something, right? That was a proofs class. It was really nasty. You had to write paragraphs with all this. Coming back. This is a proof section, but not those kinds of proofs. We just get to play with math. Can you factor? Can you reduce? Can you simplify? Can you get common denominators? And with identities. Plugging in and see what happens. We're trying to show that this is true for the purpose of being able to somewhere in the future be like, oh, hey, that guy, I can change him, and then I can manipulate that, and then it makes this possible. It's a big old puzzle. Now, some of you are waiting, thank you, because you're like, I don't want to write all the words. Can you just show me the important stuff? So the important stuff, ready? Out of this entire thing, more complicated side first. That's important. You have to stick to one side because you have to show that one is the other. And the only way to show that one is the other is to pick a side, stay there, and be like, okay, if I'm given this, can I make it that? We can't go adding and subtracting and squaring both sides. We can't be working with both sides because theoretically you're only given one and you're trying to make it into the other in future problems. If worse comes to worse, Try converting everything to sines and cosines. Number 4 is like a fail-safe. It's like I can't do anything. Okay, just get rid of anything and everything that aren't sines and cosines. Tangent, make it sine over cosine. Secant squared, make it 1 over cosine squared of x. Just get rid of everything but sines and cosines. If worst comes to worst, just do that. Number 2 and 3 are basically saying. Number 2 says, try math stuff like factoring, simplifying, squaring a binomial. Careful about that. That just means multiplying out, not bringing in a new squared. Common denominators. Number 2 says do the math, and number 3 says use the ID, use the identities, aka plug in stuff. 2 says try to do math. If you can't do that, number 3, try to plug in identities. Number 4 says worst comes to worst, sines and cosines. And number 5, to be honest, out of the entire thing, number 5 is the most important. What does number 5 say? For life, number 5 is the most important. Sometimes the hardest to do. Someone in your own words, what's number 5 saying?
Just try it.
Just try it. But go a little deeper than that, because number 5 is saying more than just try it. Like, just try it. That could be like you're at a boba place and you see some sort of weird flavor, like just try it. Okay, hold on. What's number 5 actually saying? I'm not sure just try it is the best life advice. Some things you probably shouldn't try. But
Like, even if you're wrong, you'll learn from it.
you have a task in front of you, you have something that you're supposed to do, you have something that you need to try to do. You're not sure how. Doesn't number 5 basically say you're not sure how to keep going? Because if you know what you're doing, you would never even think about number 5. Like, what's the big deal? Whatever, just do it. Number 5 says, try something. You guys have math skills. Try them. You have identities. Try to plug them in. You have examples in your notes. Try to use them to compare and contrast and see if something might spark some sort of like, oh, I think I can try. And if it ends in a dead end, if at first you don't succeed, that's discouraging them. Maybe you'll make mistakes, but maybe you'll learn from them and you won't make them the next time. Maybe you did legal math and it wasn't wrong. It just didn't help to where you were trying to go, and that's okay. Wasn't it yesterday that someone, Emma, it was you, you tried to plug in something? Yeah. I forget what it was. Oh, you tried to make sine squared 1 minus cosine squared. And I'm like, okay, but think ahead. Is it going to really help? She wasn't wrong. It was totally legal. It just wasn't helpful for this task. So just because you get it to a dead end doesn't mean you're wrong, in the sense of doesn't mean you did bad, illegal math. You probably might have made a mistake somewhere. A lot of mistakes happen in these ones because you see where you're supposed to go and you kind of fudge it to make it look good, even though you're like, I don't think that's good. But try to keep it legal, number 1, and try not to give up as soon as you get stuck. Because technically you have math and you have identities, and if at first one approach doesn't work, go back and change. Okay, so I do have a few like little this could be useful. This first one says you might not always understand why you're plugging something in, but think about that whole math step. If, for instance, you change something to a fraction, you have 2 fractions, hey, common denominator might make all the difference. So maybe you're just thinking about the algebra, saying, I have nothing mathematical to do. Oh, now I have a fraction. Ooh, I can do common denominators. Oh, maybe that can. Sometimes you're thinking of what would open doors mathematically or algebraically. Maybe the trig won't really seem like it's going anywhere, but if it allows you to take a future or an additional math step, it might be helpful. The second one says you cannot assume the 2 sides are equal. So, what you cannot do, as far as proving, you cannot square both sides. You can't work back and forth, which is so anti like all of your math training, because you see an equation, you're like, yay, I can add to both sides, subtract to both sides, multiply to both sides, square to both sides. No, not here. Remember, here the point is to start one place, start one side, you have one given, and you have to prove that it's the other side. You have to show that you can make them match, not move back and forth. And then this one's just telling you, go look at section 5.1, because some of the stuff that we do is going to unlock the doors in these problems. Long story short, we just got to make one side match the other. Start with the harder one, if possible, if there is a harder one. Play with the math, play with the plugging in, and see if you can make it match. So, this one is one that we did yesterday. I'll dual screen it in case you missed anything. Okay. That was one we did yesterday. And actually, he's a really nice one. Because this one, as you get more and more used to your formulas, wait a minute, but you don't have to have these formulas memorized when you're doing problems, right? You only have to have it memorized for the formula portion of the test, filling in the right-hand side given the left-hand side in the category. Have your formulas in front of you. So you look at something like this and you're like, oh, hey, Pythagorean. Oh, it's not a plus. Oh, that's okay. Cosine squared, I can make 1 minus sine squared, and then, oh. You're allowed to look at the other side. You're allowed to see where you're supposed to go. This section is not just like blindly sending you. It's saying, no, 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 this is what's helpful. Make it match. But sometimes, guys, you might be using the right-hand side to get to the left. Just this one, the left hand to me was a little bit harder because there was 2 trig expressions instead of just 1. But for some of you, if you're kind of like, that's easy, give me a hard one. And in any of these, you could be thinking, could I have gone the other way? Could I have gone the other way? And how could you have gotten there? Interesting question. Could have split up the sine squares to be minus sine squared, 1 minus sine squared, could have been cosine squared. Some of you that want a challenge, try to go the other way that I'm going in class. But that's an example of a T-proof. Can I show you guys really quickly, like a rubric, what I would be grading if this is a long answer on a test or a quiz? Ready? I would be grading for if you drew the T and rewrote the first step. But you get a point for that? If you drew the T and you chose a side, choosing means rewriting. And one reason I do that is because in some of these, you might start messing with him right away. And if you start messing with him right away, if you start up here, you might not remember what the original problem is without looking back. Or we might go to grade homework and you're looking at it and you mess this up, so then you don't even know what the original problem was. Remember, step number 5 says you might go a certain direction and you might end up in a dead end and need to restart. If you need to restart, you need a clean copy of the problem. So keep that, rewrite, and then you can start playing. So I'm going to give a point for drawing a T and rewriting. Sweet. I'm going to give a point if you make it match. And then depending on the length of the problem, somewhere between probably 2 and 4 points for making the legal steps. Now, here's the fun thing. Some of these have different approaches to getting there. So even if you can't connect all the dots, as long as you keep the steps legal, I'll keep giving you points. Now, I might not be able to give you all of them if you don't fully make the proof, but I will give you points as long as your steps are legal. That's kind of nice. So you get most of the points on a problem and technically not have it right. So, before we end class today, let's do one more. If you guys notice, this is number 19, which means you can probably tackle a good bit of homework tonight, because really, there's nothing new for me to teach you. There's just tricky problems for us to try together and give you more experience to go play with homework. Homework's not due till Monday. Come on. But go play tonight. Number 19. Does anybody have an opinion? Because I want to hear it about which side we should play with. Nathan. Can you explain your rationale then? Why do you want to start with the left?
The CSC is 1 over sine. So, and we have sine as a denominator in the second one, so it's just easier to start there.
Nathan in his head said, I know that he's 1 over sine. I'm pretty sure I can do something with that. You guys mind? Want to go on the left? If you want to be different, you can go on the right. Just might not be able to show you perfectly where to go. Okay, so Nathan already said cosecant is 1 over sine. Could we make a substitution right away? Yes. Could we do any math right away? Can we reduce anything? Take out some c's and some t's? But we could make cosecant 1 over sine. Did anybody see anything else that we could have done? Cotangent squared? What would you have wanted to do with him? Okay, so Nathan's just going cosines and sines. He's like, forget it, I'm just going cosines and sines. Is there something else you could do with him? Have you funny ones? You didn't have to come up with them on your own. Just put that at
1 minus secant.
Not secant though, isn't it cosecant? Cotangent squared is cosecant squared minus 1. You could have done that too. Oh, which kind of is like a, maybe I want to. So we want to do all cosines and sines or make this guy cosecant squared minus 1? I'm just showing you that different people looking at the formulas. Cosecant squared? Okay. You're just going because I said that.
That's starting at the top.
And it looks similar, yeah. Nathan's saying starting at the top. He's not putting in fractions if he doesn't have to. Could we factor the top? I guess. But would factoring make it look better? Okay, so now what? Yeah? Okay, so this guy's going to be 1 over sine of t. This guy's going to be 1 over sine squared of t. Ooh. We might not like fractions, but are we seeing some stuff happening? Okay. So how do we deal with complex fractions? We can multiply by the reciprocal of the bottom. Yeah, we could do that. So multiplying by the reciprocal of the bottom, that would be sine of t times. If you guys are curious what I would have done, I would have multiplied top and bottom by sine squared of t. I would have done my little trick of getting rid of complex fractions. But we'll review complex fractions tomorrow a little bit with numbers and then come back. Then we can distribute. Isn't that 1 over sine? Because that's mathematically legal to reduce. Sine over sine squared. Oh, guys, we're doing great because now all that's left is some math, right? We have a fraction. We could say 2 fractions. And how do we get 2 fractions together under a single fraction? Common denominators. If we had like terms, we just didn't. But if we get common denominators, then we can bring it all together. And oh my goodness, I think this is the easiest we've ever done this example in class, because we usually go the cosine squared over sine squared route, and that actually takes longer. It's gonna be a party. Go start playing, but don't worry. Tomorrow we're gonna do examples, examples, examples. We try to sharpen your skills. Bye, guys.